It's good. All right. Hello, everyone. Good evening, good afternoon, and good morning from where you're joining. Welcome to this workshop. My name is Faraz, and I'm one of the co-organizers at ML Ops. Just before we begin, I just want to give a quick note that you all would have received an email last night from Hopin. So that is a platform where all the talks are going to be hosted tomorrow and day after. Please do check your email. So the links are active. You can most certainly go into the platform right now. You can meet and message other attendees as well. So it's my pleasure to introduce Vladimir. Vladimir holds a master's degree in engineering. He became interested in machine learning and data science during his first year of study. During that time, he published several papers. He published several papers, participated in 2 grants, and wrote both his baccalaureate and master's papers in the field of ML. Since 2015, Vladimir manages the ML R&D team at WaveAccess and actively participates in ML and data science conferences around the world. So welcome, Vladimir, and over to you.
Yeah, thank you a lot. Also, I would like to introduce Aleksandr. He will be helping me during this workshop. He's our lead data scientist and lead specialist in natural language processing. Most of the questions he will be asking, he will be answering you in the chat. So if during the workshop you will have any questions at all, just write them in the chat and we will try to address them. Workshop is quite long, as you may know, so it's best if you ask them immediately because it will be hard to catch up later. Okay, so again, in order to participate in this workshop, you need to go to the chat and open these 2 links. I'm not sure if you can if you can see it. I'm only sharing the main screen. Yeah, Aleksandr just sent the links again. So one link is the actual workshop. The other is the Google Doc where we will be publishing the answers for the tasks. After you go through the link, you will see this window, and here you will have to click this button, copy to drive. This will allow you to actually do something with a notebook. You will be able to run it. After you do that, you can check that you have all of the options available here. So you can go through all of the blocks. I will just give a minute or so everybody can open the links and everything is fine, and we will proceed with the workshop. Just a quick disclaimer: I'm actually got sick yesterday, so I'm sorry if I will cough a little bit during the workshop, but I'll do my best for you to enjoy the process. And I will also be drinking a lot of tea. Okay, so I assume that everyone should be ready for the workshop. If not, please write in the Zoom chat. Alex will help you, and we will proceed. So today, today's workshop will be about exploratory data analysis and feature engineering. It's a very broad topic, it's very complicated, and in my opinion, it's the most difficult part of machine learning and data science, as it is actually what gives you the best result. You can switch a lot of models, you can try a lot of hyperparameter tuning, but in machine learning, there are many principles, but one of the main ones is trash in, trash out. So if the data that goes into the model, if it is bad, then it won't really depend what model you are using, you will gain better results, more likely. So the workshop will consists from four main blocks. First, cleaning and transforming the data, preparing for future processing, and just cleaning it and validating that it is fine to use further. Then we'll perform exploratory data analysis on the data and prepare our feature space. Finally, after we do all of that processing stuff, we will actually try and train some models to see what we were able to achieve. For this workshop, we'll be using a dataset. I think it was taken from Kaggle, but basically it contains approximately 10 or 11,000 applications scrapped from Google Play Store. It contains different sorts of data and will allow us to demonstrate different data processing and feature engineering techniques. At the end, we will try to answer the question: what factors determine the rating of a particular application and whether this rating can be predicted in advance? There is one important point that I would like to disclaim at the beginning. In order to slightly simplify the process and focus on the main stuff, we made one assumption: that we will perform all actions on the whole dataset and we'll split it into training and test subsets only before actually fitting the model. This approach will allow us to avoid writing additional code and go into these technical details. However, it is acceptable only on such educational tasks. And when working with real data, you must make sure that you allocate your test and validation and training data before you process the data set in any way, as it will lead to some data leaks. But here, as I said, yeah, we made this simplification. If at some point you will forget something and miss out, you can see there is table of contents on the left, and you can go here and look at some of the previous blocks if you miss out on something. So first of all, I'm gonna talk a little bit about the libraries. We have three main categories: it's data preprocessing and statistics, data visualization, and actually machine learning. I won't go again deep into the descriptions. You will have the workshop after the end, and you will be able to read a little bit more about all of them. It's just, you know, a description for some people that are not that familiar. So first thing we will start is we will run pip install. The virtual machine should be initialized automatically, and then the process will start. Here we're installing one of the libraries that are not present in the initial virtual machine, and we can install them right from the notebook. We'll get back to that function later, and I will remind you that we loaded it in the beginning. After we install that, we will run all of the imports in the beginning. Also, you can see here all the functions that we will be using. And we can actually start with the workshop. First thing we should do is load the data and visually explore at least, you know, how it looks. Maybe there are some things that stand out just from the beginning. The dataset is stored as well as some other files on the GitHub account. We can run this block and use those paths to later load the dataset and some other, you know, serialized functions. I will get back into it also when we go through the workshop. I should. Okay, so here we will be using pandas. Pandas uses two main data structures to store the data: series, and it is an object similar to ordinary one-dimensional array, with the difference that each element has its own index. And the data frame is a tabular data structure where each column is series. So loading the data is actually really easy using this library. We just use the function read CSV, and we can load our file data. Now, the first actual task will be to bring out the first or last 10 rows from the dataset using methods head or tail for this library. If you have any questions, please write in the chat. We will try to answer them as soon as possible. So what these functions will do, you can also specify, by the way, how much rows you want to see. So by default it's 10, but if you use one of the attributes, the amount of rows, you can output maybe 5 or 15 or how much you want. Again, if somebody has any difficulties, Aleksandr will. If somebody has some difficulties, what is? Okay. So if somebody has difficulties, Aleksandr will. Yeah, he will output the answers in the document file that we were talking before. And basically it's really easy. So as you can see, we write data frame head. And here we can, as I said, input an integer and specify how much we want out. So if I print 3, we can see that there are only 3. If I input tail, for example, 20, then we will see the last 20 rows. It's it's usually a good thing to look at the data in this way, just to understand if it's correctly parsed, and you can go on working. So the dataset has multiple columns. It's application name, category, application rating, application size, type, price, content rating, so the age group for which the application is intended, the genres, subcategories to which the applications belong, and current and Android version. Yeah, so it's this ID. Okay, so Alex said correctly. So the data frame objects usually have dual indexing by columns and by rows. To specify a specific row, you can use the log function. It returns rows by given index, or ilog. It returns rows by their positions in the dataset. So I will just say that it is important because in the beginning, when we just load our dataset, all of the indexes, they go one after another. But if we remove a row from the dataset, the indexes will not be recalculated unless you specify so. So we might end up, for example, if we use head, if I remove the first row, then the first index will actually be 1. And after that, the ilog and log functions will return different results. But so far, you can see if we use this function, we will see what the contents of this row are. And also all of the details regarding what object it is, what type it is, and its name. Next, when outputting the information, we can output only a specific column. So here, for example, we specified that we want to see only the first 5 rows of the column called app. And finally, the quickest method for data selection, if you want some specific selection for one element, you can use this function at, and it will give you For example, for the first row, it will give you the value of this column. Data frames can work quite long if they're big enough. So sometimes if you need something specific, it's better to use this function. It's not exactly the data processing itself and feature engineering, but it is always important to remember that if you're working with huge data sets, it's really helpful if you use optimal solutions, because it will allow you to work faster. So now, if we need to select several columns, we can just do it by feeding a list. And here you can see we output the first, well, not the first, second to fourth rows, and the app and category columns. You can do the same with ilog. Yeah, and here, by the way, we're using the indexes of the columns. It's not specifically necessary to use their names. If you need some strings that match a condition, you can also do that after the data frame. We have this parenthesis, square parenthesis, and inside we specify that we want only those rows where data frame category column is equal to art and design. And if we run that, you can see that the category is as follows, and we can basically have this subset if it is needed. For complex conditions, it is placed again in the parenthesis, and we use the and or operators, and we can see here, so the rows where the category is art and design and the type is free. So here. It's really helpful. It's much more convenient to work this way than with usual dicts, because you can operate the data, you can sort it, and you can do all sorts of stuff. Finally, we have the data frame info. So after we loaded the data frame, it's again, we need to look at what does it contain, so to verify and validate the data. Info is a really good first step to do this, because first it specifies what type does it contain and how much rows does it have. As we can see here, the dataset consists of 13 columns, and I don't know. So here, all of them are categorical. I'm not sure actually why there is one float, but nevertheless, it's not as important. The key thing is that we can see here that, for example, there are multiple columns that have missing values, and we will have to address that in the future. Also, pandas has many built-in functions for working with data, and you can learn about them here. There is a link. One of the few that I would actually want to point out, there is such thing as a pandas profiler. Alex, if you could be so kind, can you please write a link in the chat? So pandas profiler, it's basically it does some data analysis and EDA automatically. It definitely cannot cover everything, but again, it's a really good first step to use the minimum amount of code and get the maximum result with very few efforts. We're not going to use it here because the main point here is to actually do the things ourselves, but you should definitely know about this method, this functionality of pandas, and use it if you ever work with such data. So now we will proceed with exploring the data. The main the data may contain incorrect or missing values, other artifacts. Moreover, types may not match the content, and in order to proceed, one must find it and correct all errors. Actually, data validation is a very complex question because there are really tons of different things you can check for. It's not only about the data type or missing values, it's about the correctness of the range. So if we see maybe, I don't know, a negative age, it's not appropriate, or maybe an age of 100,000 years. So we understand that it's not correct. Outliers, completely missing rows, and we can do that if we have an external index, and we sometimes can see that some rows are missing for some reason. The formats, so the data, as you know, data can be written in, I don't know, there are so many formats for that, and you must be sure that it is consistent in your data set. So here we will go through each column and try to validate and fix the data that we have. First, we will go through the category. So the category, if you remember, it's a column that specifies what exactly the type of application it is. So if we look at value counts, it's a method that uses that calculates the amount of occurrences for each unique value. And as you can see, most of the occurrences for the first three is family, game, and tools applications. The other more distributed more equally, except some of the lower ones, and there is definitely one application in the two category, and it's most likely an outlier. There is some mistake. So it does not make sense. The name does not make sense since it's the only one. So we can use the method that we talked about before, and find the row in the data frame where category is equal to this value. As you can see, it mostly looks fine, but what actually happened is that there was a shift of a row on one column to the left. Because this leads us to losing the category, and it's only one row, it's better to just remove it and forget about it. It won't affect the solution in general. Okay. So now, if we do it like so, we can pick every row where the category is not equal to this value. Now, you can check for yourself if there are some missing category values in this column. You can use the methods isNull and sum to do that. I will give you a couple of minutes so everybody has a chance to perform this task, and then Alex will again output the resolution in the document. Akshay, so yeah, so if you already ran this block, then here we override the contents of our data frame. If you want to double check, you can click on the previous block, and in the runtime, you can use the run before function. This way, the notebook will go through all of the previous blocks, and you will be able to check again that the data frame actually has this row. And here in this 21st, in this block, you will be able to remove it again. You can see, yeah, so run everything before. Yeah, and as you can see, it is here. Then we run this cell, and if we run this again, you can see that we do not have it. No problem. So ask any questions you want. Yeah, so let's wait one more minute and Aleksandr will write the answer. Of course, let me, yeah, thank you, Aleksandr. And Daniel, please make sure that you click on the make sure you click on the run copy to drive button. Otherwise, you won't be able to run the notebook. Okay, so let's proceed for now. So one way to do this is to just get the isNull function. And initially what it outputs a Boolean value for all rows if it is missing or no. And by adding sum, we're calculating on all true values. But here we do not have them, so nothing to worry about. So the next column is rating. It's our target column. It's really, really important to check that all values are correct and that we can actually use it. So, and right from the start, there is the next task. You have to calculate what rating does the majority of applications have. Just to clarify, you can look back. We already did it previously on the last column. Okay, so here we won't spend a lot of time because basically you can just copy the previous solution and input the correct column here. And as you can see, our data set is more or less balanced. The second class has the most occurrences. So basically, we have three classes. 0 is a bad application. 1 is like a normal one with mixed reviews, and 2 is a good application with good reviews. And the next thing that we can do is to visualize. It's a pie plot, and again, sometimes it's easier to process things visually. And here we can see that, yeah, it's again, it's mostly the same. One more thing that you could do is to use the describe function. The describe function, it calculates the distributions for the specified column. As you can see, we have 3 unique values. The top one is 2. The frequency for that top value is 4,411. Sometimes it can give a really, really good insight regarding the distribution if we have some numeric value, numeric column. It will also give the percentiles, it will give maximum and minimum values, and it's sometimes good to spot some outliers if something goes really wrong. As I said, for example, if we had age, for example, it would be a really good way to check if we have some values that do not feel correct. So again, we're checking for missing values, and we don't have them for this column. Next, we have size. The information contained in size is clearly numeric. However, if you remember, the column is categorical. This is because we have special characters. So as you can see, we have the M character for megabytes and the K lowercase for kilobytes. This does not allow us to treat this column as a numeric one. And this leads for how many? So 461 unique values. It's not right. So in order to fix this, we need to replace some we need to replace these characters. And again, do not forget that 1 megabyte, it actually contains 1024 kilobytes. This task is slightly more complicated, so I will give you a little bit more time. If you have any questions, you can ask them in the chat. Here, I would like to also point out that in the first block here, you should write the code for the method, for the function, which will receive one of the possible values of size to the input and will return either the corresponding number of megabytes or a non-value. Actually, sorry, I think that the second block with write your own code here, it's just a typo. There's only one block here. So all you have to do is write this function here. We will use it later. Okay, so this task was slightly more complicated, but the general logic is quite simple. We get the value here from the column. If we have an M character in the size value, then we just remove it. If we have a K lowercase character in the size value, we make it float, remove the K from our row, and divide it by 1024. And in case we have something else, we just replace it with not a number. So now let us check if it works. Now, after we use the apply function, so it's something that you can do with data frame. You can write a function, for example, here, check size, and you can use the apply method for the whole column or for the whole data set, and to apply this method, this function for each row in that data frame or series. After we've done that, and if we look at our data frame size type, now it's considered as a float. This is what we actually wanted to do. All values where we had variations with device, if you remember, those were the first ones, the biggest one. They are right now considered as considered missing. This is because we cannot actually tell what exactly was there. But as you can see, about 16% of our samples have missing values now. That is quite a lot. And to deal with this, we can create a new column with binary values that will store information about these missing samples. And then we can process them in the original column. This is done because if you just fill the missing values in the original column, this can pretty much skew the distribution and mess with the model, how the model perceives the result. But on the other side, having a separate column that tells us which values were original and which ones were somehow imputed there, we can the model will work just fine. There are multiple ways to handle missing values. Some of the traditional methods are actually removing the row, but here we have about 16% of missing values. It's really a lot, and it's not a really good idea. We can replace them with an average, mode, median, or zero, some fixed value. We can replace them with nearby examples. Mostly it is applicable for time series. We can use the distribution of existing data and use it to generate new values for features. It is useful when we're working with linear models, because this way we're not messing with the distributions. Because imagine if we, for example, use median and apply it to 16% of the data, the distribution will have a really sharp peak, sharp extremum value in the middle. And linear models do not really like that. If we're using something like random forest or something like, or maybe gradient boosting, so decision tree based, for example, it would not matter. And finally, we can make this column a target variable for a separate task and train a separate model to predict those missing values. It all depends on what exactly the missing column is, and can we somehow extract the information of what should be there. But again, the easiest option would be to delete, but usually it's not a good one. So the best way is to use a special model. Again, it could take a lot of time. So right now we will use the median. And the next task will be to change the missing values with the median of that column. You can use the fill NA and median functions, and you will be able to do that. Again, if you have any questions, please write them. Okay, so again, this is somewhat slightly more complicated, but as follows. So we override our column, and here we use the fill missing values, and in the parentheses, sorry, in the parentheses we specify what should we how should we replace the missing values. And here we use the median of our column. And if we look now, there are no missing values here. So just a quick question. Does everyone, is the pace okay? Or so basically, can you keep up with the process, or should I slow down and give more time for the tasks? Okay, it seems that okay. If somebody has some issues, then again, please write. The next column is type, and here, as you can see, almost 93% of our applications are free. To say more, we need to take a look at the relationships with other variables. We will deal with this in the next section. But for now, we will just check if there are missing values, and there is actually one. So again, we can deal with this just as follows. I think we should do it like so. Sorry. Let's just make sure. That's odd. Oh, okay. It's slightly different. One moment. Okay, so everything looks fine. I think there is a problem. Oh, sorry. It's actually the next task. Almost started doing it for you. So here you have to do it on your own. You need to remove this missing value that we have over here. Sorry, oh, I completely forgot about this. So here we'll have a couple of minutes. While you're doing the task, I will remind that we will have 3 breaks during this workshop. The first one will be in 10 minutes. It will be a 5-minute break, so everybody just can grab a cup of tea or drink some water. The other one will be at 11:05, and it will be a 15-minute break. So I don't know, you can maybe get something to eat and do all your stuff. And we will have a final break at 20 minutes past 12, and it will be a 10-minute break. So, okay. Okay, so here there is a slightly unorthodox solution. So what we do here is we take our missing row and we check where we have a free type. After we do that, we can just use the sum function as before. As you can see now, our data frame does not have any missing values. So, okay. So next is the price. So here, this variable is numeric, but it again contains some special characters. That's again why it has an object type, as you see before. If we remove the special character of a $sign, we can change the column type back to float using the method asType. Yeah, there's something wrong here. Let me just, one moment, I will rerun the notebook. Okay, now it's fine, sorry. I think I messed up while I was filling in the previous task. So yeah, as you can see, there is a $sign in the beginning. And it prevents us from treating this column as a numeric one. So the next task, the task number 7, it is about removing this special character, and after that, changing the column time to float. We already did this before with another column, so you can just look back and see how it can be done. Okay, Sandra, I will. I moved my mic, so I hope that you will be able to hear me better now. Okay. Okay, so here it's slightly easier than it was before, actually. For this column, we can override it by replacing the $sign with missing value. And then for the whole column, we can just apply the asType method and change it to float. Now let's see a distribution plot of prices. Okay, and oh, I didn't actually run it. Okay. As you can see, cheap applications make up the most part of the distribution. And moreover, the rest of applications take a very small part of all applications. So it's difficult to say anything by this plot. So we can actually apply the logarithm. The logarithm function is really useful when we have this extreme-like distributions, and the logarithm will smooth it along the range that we have, and it's much easier this way to just look at the data. Most applications cost between $1 and $3. Well, logarithm, of course. And the distribution of values on the left part of the plot is due to the strong discreteness of small values. But let's look just at the strange peak that we have on the right side of the plot, if you can see here. So the price there is above $200. And as you can see, these are some really strange applications for which just to brag about that they have it. I'm not sure if you ever heard about them, but I did. I don't know, maybe it's some indicator of status, something like that, but it's really not usual, and they are most likely can be considered as outliers. But we will deal with them later. Right now, we'll just check that we do not have any missing values here, and we don't. And we can, I think we can, yeah, we will go through the last column before the break. It's about content rating. We use the value counts method to get the estimation of how the data is distributed. As you can see, most of values lie in the everyone category, but there are two categories, unrated and adults only, that have 5 total applications. There is no chance we can do anything with them, so it's just better to remove them so the model does not try to fit to them. After we do that, as I said before, by using the logical operator AND, where we pick all of the rows that do not have adults only 18 plus in the content rating and unrated. Now, if we double check, we can see that we removed those rows and we have only 4 categories left that we can work with later. And just a quick check that we do not have any missing values. Okay, so right now we'll have a 5-minute break so everybody can drink some water and I don't know, maybe do some stuff. And we will get back to the process at in 5 minutes. Okay, so please do not be late. Okay, so I hope everybody is back. Let's get back to the process. So next we will go through the genres. Here, as you can see, there are quite a lot of unique values. And moreover, some of them are actually a result of combining 2 basic genres. Let's find out the amount of unique ones. So here we just divided those that are together, and we can see that we have 53 subcategories. Now, in order to estimate the general distribution, we need to calculate the amount of genres for each app. You can use the series string find all in order to do that. So I will give you maybe a couple of more minutes, and then we will proceed. I must notice that I don't understand that going through these columns could be a tedious job, but this is actually how things are. And in each case, we may encounter different problems, different things that we need to deal with. And that's why we're going through each one of them. Afterwards, there will be some more, let's say, action. But right now, we will go through these ones. Okay, so I will add the task right now. Okay, one moment, I will edit. Okay, so here we use the string find all method, where we find all of the cases where we have this character, and then we just apply ln +1. This way, if you see, right now we can consider this as we can count the distribution. And yeah, so there isn't a lot of applications where we have a lot of genres. So here, basically, what we can do is just look at what kind of genres they are. As you can see, it's art and design and pretend play, stuff like that. You may notice that the genre column often contains the same first value as the category one. We will explore this in more detail later, but right now we won't do anything about it. But we should remember that there is a problem. But for now, we'll just check that we don't have any missing values and go on with other columns. So the current version is mostly consists from unique values. It's very likely not to be an informative column, and it seems that each developer uses its own notation, so we will just remove it. And sometimes that's something you should do, because leaving a column that does not make sense, it can be harmful for the model in the end. So we just use the drop method, and we specify that we want to drop the current version column. The Android version on the other side is slightly different. Here, if we look at the distribution, we see that there is some pattern to it. After checking for the missing values, we have 2 of them, and we will just remove them. But regarding the other, the not missing values, as you can see, there is a primary version in the beginning. So it's 2, 3, 4, 5, 7, 8, and stuff like that. Sometimes you can scale up the classes. You can combine classes from inside the column if it makes sense. So here we will just this loop. It combines all of the versions by themselves. So version number 1, 2, 3, 4, and stuff, without any additional indexes. But still, groups 1 to 3 and 5 to 8, they have a really small number of examples. This is also a problem, because when we have a lot of categories, and some of them are big and others are small, the model can override some of them, and they won't just take into consideration some of the small classes. So here we will just combine some of the classes, and now we have versions 1 to 3, version number 4, it's the biggest one, version number 5, and higher, and some that vary with device. Now, each of these columns, each of these classes, they have a statistically significant amount of samples that we can further work with them. Again, double check that we do not have any missing values, and the final check that in general we do not have any missing values in any of the columns. Finally, we need to remove the duplicates. you won't always encounter them, but here we just at first we need to make sure that we have them or not. And if we search for duplicates, and if you can see, if we look for the subset of applications, we can see that there are some. And duplicated applications, as you can see, there are 3 applications that are called box, 2 that call blocker, bubble shooter, word search, and it's not very helpful for us because again it will mess with the algorithm and it's really not useful. So it's a far-fetched solution, but so far we will just take and sort them by size and remove the duplicates, leaving the largest one. It's not specifically, there might be other solutions, but considering that they all are called the same, it's really hard to understand which one is better, because the Android version and the version itself, it also doesn't tell everything, to be honest. So here, as the next task, you need to remove the duplicates with the drop duplicates method and keep the applications with the largest size. Okay. So here it's pretty much straightforward. We use the drop duplicates, we use the subset with the applications, and we keep the last one because they are sorted based on their size. This will leave us with only the last ones, the biggest ones. After all of that, after filtering all of the missing values, filtering the duplicates and stuff like that, we lost approximately 11% from the total volume of our dataset. Obviously, it's a very unpleasant measure, and you never want to do that if it can be avoided. But this time it had to be done. As I said before, the application versions, when we prepared this workshop, they did not give any insight regarding the differences. So it had to be done. And now everything seems to be fine. Here we finish the part where we go through all of the columns. And now we can get to actually exploring the data in terms of the data insights. A moment. Okay. Yeah. Sorry, I forgot to run the cell. So now, first thing we will do is to process the numerical features. One of the simplest and the most effective ways to deal with this is correlation analysis. Correlation analysis is a statistical relationship, and it can be somewhat difficult sometimes to comprehend. Here you can see the linear correlations. If we there are actually multiple ways you can calculate them. There are several criteria. The most oftenly used one, the most often one that is used is Pearson correlation. It just determines if there is a linear correlation between columns. There are also such things as Spearman correlation that determines some non-linear dependencies, but only specific ones. It's not always, it will not be able to always grasp all of the nonlinear dependencies. And there are also several criteria to process categorical data. But so far, we will just use the simplest one, the Pearson correlation. And here we can see we have 3 numerical values. And they are not really correlated between each other. And it is actually a good thing, because if columns correlate with each other too much, it means that they either duplicate each other, or if there is a really strong correlation between feature and the target variable, it means that there is basically a leak, or there is a really simple explanation. Usually it's the first one. Usually it's just a leak. So as a next step, we will use the pair plot method for our numeric variables. A pair plot is actually somewhat more difficult to process, especially if you have a lot of columns, numeric columns, but it can give you a really good understanding of how the data is related to each other. This time we will make a separate data frame for this, and we will just take specific columns. By default, one moment, it has to calculate. By default, pair plots, you have the distributions on the diagonal, and it uses the kernel density estimation. But the problem is that the kernel density estimation, in some cases, it does not work well. Instead of smooth bells, sometimes there are high peaks, ridges, and there are other artifacts. So that is why usually I prefer to use histograms. But it's on the diagonal. On the other side, you can see the distribution between different values, different features. So here we, for example, have a logarithm of the price and the size. And also we use hue to highlight which classes do we see and what can we elaborate from the distribution. So just to give you, some like an open-ended task, can you look at this plot and try to make some assumptions and some conclusions from what you see on this plot? I will add some of the possible answers later, but here actually there could be a lot of things that you could find on your own. If you have if you have any suggestions, you can write them in the chat for this task. And don't worry, don't be shy or afraid. I'm quite sure that everything you suggest will be fine. Yeah, so this is actually a very Interesting point. But the problem is here is that these plots, they do not, if the points, if the samples exactly match each other, it could be hard to distinguish if there is actually one or multiple points here. But it is definitely something that you should look into. So yeah, it's a good point that it really stands out here. So the other things that you could notice is, for example, that applications with small size and small rating, the 0, 1, they are more frequent for small applications, as you can see. So if the size is small, we have more and significantly more bad ratings for these applications. The other thing is what really stands out is that we do not have big applications. So as you can see, the size. This part of the plot, it is empty. We do not have expensive applications that take a lot of space. Also, applications with good rating, the 2 rating, mostly have low prices, and the peak on the second basket probably occurred due to the replacement of missing size values with the median, as you can see over here. And the applications with a good rating also stand out among the applications whose size depends on the device. Again, it's a very open-ended question. What could be found on this plot, but it's always good to get this feeling of how these variables correspond with each other. Now, for the application length and rating, let's see how the length of the application name affects the rating. It's a really strange feature, but you will see that it actually, in the end, you will see that it actually, for some reason, it made sense. So if we calculate just the amount of characters the application has, you can see that applications with small number of characters in the application, they have a significantly bigger amount of negative reviews. And on the other side, the applications that have a lot of characters, they are more likely to have good reviews. I don't know actually why is it so, but the distribution just tells the story. So sometimes it's just an example of that sometimes you really do not know what the data can consist from and what insights can be important. So it is strange, but it makes sense considering this plot to implement this as a feature in the future. So now the price and type. It is logical to assume that if type is free, then the price should be equal to 0. So here we use the group by method, and it allows us to calculate the mean. So the mean for free applications is 0. So it makes sense and everything looks fine. Again, it's just double checking that the data is correct. Now we can take a look at the category and genres. If you remember, we were talking about the fact that the genres and the category often correspond with each other. But here we will aggregate categories and genres in a separate table and make a new column with the number of genres. So basically what we did here is we have the category, we have the genres, we have the rating, and we have count of genres. This will allow us to create a separate column that will not duplicate the category as itself, but still will have some information left in it. So now, as the next task, you can explore the general number statistics for each category. You can use the group by and describe functions. If the task itself is not completely clear, you can ask in the chat, and I will elaborate a little bit more. The tasks from now on are going to be slightly more complicated, so I will most of the time mostly give somewhat more time to deal with them. Yeah, okay, no problem. Yeah, it's actually, if you guys will write the chat, it will be helpful to understand when we can move on. For those who actually already finished the task, and while we're waiting for others, you can, for example, take a peek at the following blocks if you want. Okay, so this is a slightly more complicated task. So let me describe here what we're doing. So we're using our data frame that we gathered on the previous block. This one with a category, genres, rating, and number of genres for each row. Then we group them together by category and count of genres, and we use describe. After sorting the values, we can see that, for example, for category parenting, we have 60 samples, and for this category, mostly it's the biggest one in terms of having multiple categories. As we go further, the percentage declines. The family is the biggest category at all, and it has a mean of 1.18. And here again, we can just tell that it has quite a few categories with multiple. Sorry, it has quite a lot of genres with multiple subcategories. Only 11 categories in general have multiple genres in total. So they often actually overlap each other. And we can actually study this in details. For starters, we should bring categories and genres to a common format. So we need to transform them into lowercase and remove special characters. In other words, replace the special characters with spaces or nothing using a string replace. Here we have quite a few operations that we perform. So basically, we make both of these columns in lowercase. We replace all of the special characters, and now they should be they should look the same. As you can see, now they look really similar. Now we can calculate how many applications have exactly the same genres and categories. Here we just calculate the sum of genres and divide it by the length of categories in our data frame here. So in almost 70% of cases, they are completely the same. That is that in 70% of the values do not contain any new information. Most likely that there are even more matches, consider possible errors related to usage of regular expressions on data. Not regular expressions here, but it can be used. But anyway, we can deal with this by adding a separate column. And it just can tell us whether the genre is equal to the category or not. It will be a binary column, as you can see here. And it's much more informative in this regard than just keeping two almost completely similar features. So the next task would be to explore whether there is a difference between the distributions of applications with the same and with different categories and genres. So this will basically give us an understanding if having multiple genres can affect our distributions and our results. Okay, so was anybody able to finish the task so far, or should I give you some more time? Okay, so I will give you a couple of more minutes to finish it. Okay, yeah, I will. I'll give I don't know. Let's say 3 more minutes, so maybe people will be able to finish. Yeah. Okay. Of course. Task number. Okay. The 12th one. Okay. So here, as you can see, we have this data frame, def cat genres. We have category genres, rating for these samples, count of genres, and is the current category equal to genre? So as you can see, these are equal and we have true, these are not and we have false. So the question is, if there is a difference between distributions of applications with the same and with different categories. So if we take all of the samples where the library, where the category and the genre is the same, so basically this column is true. And if we take all of the samples where this column has a false value, if we compare their distributions, will we see any difference between them? Yeah, so yeah, sorry. The difference between distributions based on the rating, because this is our target column. This is where we should compare them. Basically, if we have the same category genres, does that affect the ratings compared to different categories and genres? Okay, let's proceed. So as you can see here, we built our plot, and we use the SNS count plot as this distribution counter. So here, first of all, we have our column based on which we compare them. We use hue on our rating column, and we use our data from the data frame. Now, here we can see and estimate if there is any difference. So the distributions are actually slightly different. We can see that the application with the rating 0 stand out a little bit over here. We have more bad ratings where we have the duplicates, and where they're different. It's more like it's increasing towards a better rating. To numerically estimate this distribution, we can use the contingency table. It's not a very popular instrument, but it is actually really good to sometimes evaluate the results. Basically here, what we can see is that we have the values for each rating for false and true. And here we can estimate the correspondence between these different values. So the difference in the distributions for applications with the same category and genre is negligible. On the other side, if applications have different genre and category are if applications have different genre and category, they're 1.5 times more likely, 50% more likely to have a good rating. Such column would be useful in predicting the rating of applications, but at the same time, there is actually little sense to leave two columns with almost the same information. This is why we will remove actually the column called genre and add our column is cat equal to genre and proceed with it. So if we do that, one moment. Yeah, so this error is because I processed the cell twice. So if we look at the head, you can see that we no longer have the genre column, but we do have a new one, is cat equal genre. Next, we will deal with rating and content rating. First thing you need to do is explore the relationship between rating and content rating columns. You can do that again by looking at the previous blocks we did and try to use the same approaches here. You can actually use different sorts of evaluation techniques. We went through quite a bit of them already. So it's up to you actually what exactly you will use to gather information about how they correspond to each other. Okay, so any success? I would also remind you, if you have any questions regarding the task, or if we're going too fast, you can write in the chat and ask all the questions, or maybe ask to give to have some more time for the tasks, because everybody here has different levels, I assume, and it's important that everybody can keep up the pace. Okay, so there are actually multiple ways to do this. The first one is, as we did before, to create a plot of to the distribution of applications by ratings. Here we can see that mostly, as you remember, all of the samples are in the everyone category, and the others, they have somewhat similar distributions in terms of smaller amount of bad ratings and bigger amounts of good ratings. We can also use the cross tab. We can also use the cross tab variant that we looked at before. So as you can see, mostly the zero rating is most likely to have the everyone category is more likely to have a zero rating, and the teens, and everyone plus, they are more likely to have a good rating. It's also actually important to understand all of these parts, because it will define how exactly we will process our data further. And finally, we can build the pie plots, for example, and see at the distributions this way. So here is it's much more evident, as you can see, that that everyone plus is more likely to have good ratings, and that everyone is well, it's mostly equal, though it is slightly more important here, especially compared to others. So now we will look at the table of both rating contingency with content rating column and the is not equal genre. First thing that you could notice are that the applications with the age rating of everyone are in the same categories and genres. So as you can see, for everyone, it's mostly the same over here. It does not vary at all. But for everyone plus, there is a big difference in the false and true points on the column that we mentioned before, the is cat equal genre. And it can be seen on others to everyone 10 plus, mature, teen, everywhere where we can see there is a difference in the distribution. So it again just confirms that this column could be important for our results. So now we'll go forward with the category and price. Another convenient way to explore the data distribution is a cat plot. In its simplest, it allows you to display each individual example in an individual column. Thus, you can get a sense of the data density. We will use previously generated logarithmic price column and consider only paid applications. So, as you can see, there are not a lot of paid applications, but numerous categories. So the graphics, so the plot is quite sparse. You can also see that for some categories, we have outlier applications. For instance, communication category, where is it? So over here. Communication category, mostly grouped together, but one stands out from the others, this one. Finance and lifestyle are also quite sparse. Note that the family group, here, the family group contains a group of detached expensive applications. Now we will take a look at the same distributions, but using confidence intervals. Confidence intervals is a separate instrument. It can be slightly complex, but actually nothing too difficult. It is a type of interval estimations used in statistics that are calculated for a given level of significance. They will allow us to make a statement that the true value of an unknown parameter is has a significant amount of statistical, a good amount of statistical significance. So the practical meaning for this is that a wide confidence interval indicates that the sample average doesn't accurately approximate the general average. We'll better see it over here after I build the plot. So here you can see that we have these levels, and the black line basically indicates the inconsistency. How wide do we have, how broad is the variance of that specific category. What stands out the most is that for the events, it's really, we do not have any variation, but the problem is that for the events, we have only 1 point, and this is why actually we have this. In other cases, we can see that the finance and lifestyle categories have a very wide confidence interval over here. And it's not really good. This means that these categories are highly sparse, and they have some isolated groups in different parts of distributions. It is not valid to use the average value of such categories to approximate them. So in order to look how the expensive applications in categories for finance and lifestyles work, we will build a separate plot, separate statistics, sorry. So here, here you can see that for lifestyle and finance, we have 36 samples, and actually the standard deviation is quite big. The problem here, if we go back and we get our log price, we go back to those applications for I'm rich and stuff like that. And this ends up being a problem because they skew the distribution, and it makes us much harder to process these columns and the dependency between these columns. So what we will do here is we will just rearrange these apps, we will remove them and calculate the plot again. As you can see, for these two parts, it's much better now. The social is still not very good, but if I remember, yeah, the social also has only 2 points, so there is no sense of actually trying to deal with them. As you can see here are those applications that messed with our distribution. After we removed them, everything seems to be in order. Now the lifestyle and finance categories became more realistic and stable, so we're removing the extra expensive samples that we've talked about. And finally, we will just look at the category and size correspondence. First, we will add the logarithm of size to data frame log. It will again help us to deal with the exponential growth and handle the process better. And for your next task, you need to explore the distribution of application size to each category. And you should use the data from log table, the one here, and the logarithm size column. Also, right now we will have a big break, a 15-minute break. So you can finish the task, and I think we will proceed later at 20 minutes past 12, if I remember correctly. Oh, sorry, 20 minutes past 11. While I will be here during the break, and if some of the things that we've talked about during the last 30 minutes were not very clear, I will be here and you can ask them. I will do my best to explain the things that you've missed. And I will turn off my video for now for the break, but I am here if you have any questions, write them in the chat, please. Okay, guys, so we're gonna wait for anybody who might be still not here yet. And we will start in a couple of minutes. Okay, guys, so we'll proceed. So here on the last task we talked about, we use basically the same code that we used before, only for the log size column. Here, basically, everything looks fine. The distributions are, we basically do not see any major outliers and stuff like that. Maybe in some cases for dating, for example, here, but it's not that important, actually. There are no major outliers like there were previously. Okay, sorry, I forgot to turn on my video. So now we come to actually working with the feature space. And here we will first create a table where we will store our results. it is important because we will be testing a couple of different approaches, a couple of different models, and we will be able to just store the results so we can look at them further. To measure our processing time, which is also usually really important, we will add a special context manager that is defined as a class. And we will create an object of that class, which we will be able to use further. So the first thing you usually want to do is to create a baseline model. Our task is to determine the rating of the application. So we will just take this column into a separate variable and remove it from the main data set. It is required so we do not send our target variable to the training part. First, we will use the so-called majority classifier. It's the simplest way to build a baseline model, and all it does is just takes the class with the most amount of occurrences and just estimates as if everything has the same class. That is why it is called the majority classifier. It's not something. It just gives you an estimation from that you cannot go lower than this classifier gives you the results. Sorry. The main point is that some datasets, they are not balanced. Ours is mostly balanced, but still one class has about 1,000 samples more than others. And if you end up having a model in the future that gives you an accuracy or I don't know, something else worse than this baseline classifier, then you clearly did something wrong. It's just a good indicator to start. So we use the train test split here. I again remind you that you should usually do this in the beginning before everything that we did previously. You should do the train test split. The problem is that you will have to add additional code to implement the fit transform interface that is usually used, for example, in scikit-learn. The fit transform interface, it allows you to calculate and get the parameters, get the data preprocessing stuff based on the training data. And then after you do that, you have the transform feature, the transform method that will apply all the weights, all the preprocessing functions that you did on the training dataset. It will apply it to the test and the validation datasets without actually taking any information from them. It is really important, but here, as I said before, it's just a simplification. Okay, so yeah, we already did that. So the most common class in our data is the second one. The training set samples with the second class are more common specifically. So our baseline prediction will be basically just saying that all of our predictions are from the second class. Now, to analyze the results, we will use a function that displays several different metrics. Here we will use the accuracy of one scored, the classification report, and the confusion metrics. Sometimes you will want to see more. Here, it's the bare minimum. First of all, you never want to use only accuracy because it's not something that you can usually account for, as again, it's really depends on the data balancing. The F1 score usually is one of the most important scores because it takes into consideration the difference between the number of samples in the data set. The key point here is that actually the F1 score depends a lot on what value in the target column we take as the primary one. And therefore, we have different F1 scores for each target class. There are multiple ways to average them. There's a macro average, micro weighted, and stuff like that. Usually, I prefer to use the macro average, as you can see that there is a slight problem with the weighted one. On the one side, it just averages out the F1 score, but it does it based on the support, not based on the real occurrences of the data. So here we have an F1 of 51%, while all of our samples are in one class. It's not really good. So that is why usually I prefer to use macro average estimation of F1 score, because it gives you a much more realistic evaluation of your results. So these will be our reference numbers over here. We will add them to the dictionary to the list that we implemented in the beginning, so we can compare it later to the other results. Now we're going to use the original feature space to predict the target variable and measure the accuracy of the prediction. We will only use the numeric and Boolean features, so they don't require preparation, unlike text. Again, it's the next step from the super basic classifier to something that is already implementing something from machine learning, but again, not actually taking any preprocessing and feature engineering, so we can again evaluate the progress. If we look at our data set right now, we have two float features and two Boolean features. Others are objects, basically categories of text. What we will take right now are only the integer and Boolean features. It's not a lot, but we will just try to make some predictions from them for now. Again, we perform the train test split, again, because we use different features than before right now. And we will apply the logistic regression model. As I said before, it doesn't actually really matter well, it does matter, but it's not as big of a deal what exact model you're using most of the times when you're talking about structured data. And there are, of course, different cases of applying gradient boosting, neural networks, and stuff like that, etc. There are a lot of algorithms, but the main part is how you prepare the data, because it doesn't take a lot to just go through different algorithms and tune the parameters and just process in time. So logistic regression usually works really fast, so this is why we will stick to it right now. But again, after the workshop, you will have the notebook itself, and you will be able to also test for yourself how different algorithms affect the results. Logistic regression itself is probably one of the simplest classifiers, and to perform hyperparameter optimization for it, we will use cross-validation by applying a pipeline and grid search CV functions. This classifier, as I said, was chosen because it is fast. And I think we added some more complex models results in the bonus section, but we will get back to it further. For linear models, it is really important to scale the data, to scale numeric data. The reason for this is because originally, if we have our feature space not scaled, different features and the feature space itself, it is very stochastic. It can basically, when the tuning process, when the model is learning, it tries to find the local minima of the error. And if the data is not scaled, it can go in, let's say it in the wrong way. It can take much more time to train on an unscaled data just because the algorithm has a lot of problems finding the right way towards the local minimum. However, it's not important on non-linear models such as such as random forest or gradient boosting. They don't care at all about data scaling and stuff like that. One more thing that is important, why it is important to scale, is because logistic regression is basically is just a superposition of our features. So basically, we have coefficient for feature number 1 multiplied by the value of feature 1 plus coefficient multiplied by feature 2 and stuff like that. So if our numeric variables, if they have different scales, for example, one is from 0 to 1 and another is from 0 to 10 million, the algorithm will have a lot of trouble actually tuning the parameters, tuning the coefficients for them to work properly. So here we implement our pipeline. The pipeline basically tells us what we want to do and in what order with our data and with our training sequence. So here we add our standard scaler. It is a feature, it is a method from scikit-learn that will scale all of our numeric data. And then we apply logistic regression. The parameters that we want to go through are the classification C value, which basically affects how the model will tune its coefficients, and the penalty that we use. So logistic regression has these regularization methods. It's lasso, reach, and elastic net. They are required in order for the model not to overfit. The lasso, the L1 regularization is it basically reduces those features that have low coefficients that are not important, and it can be used for feature filtering. The L1 coefficient works in a different way. L2 coefficient works in a different way. It uses square 2 norm. Sorry, my cats are fighting. So it uses the square norm. So it does not filter the coefficients, but it makes sure that none of the coefficients are too big. It penalizes those coefficients that went too high. And the elastic net, it basically combines both of them. These are the parameters for our cross-validation process. So grid search CV, it basically applies cross-validation on the grid of our parameters that we set for us to evaluate. So it just has this metrics from these parameters, and it tries to find the best hyperparameters for our model. Okay, so let's see. Yeah, it should work. Yeah, and here, after we defined our pipeline, after we defined our parameters for the grid search CV, so here you can see that we allocate 3 folders for our cross-validation. So a quick side note, cross-validation basically means that we do not allocate a separate validation dataset, and we use our training dataset by dividing it into separate parts, and we run it several times. For example, if we have 3 folders, then we run our training sequence 3 times, each time validating on a different folder. This way we avoid spending, we do not have a lot of data. And because of that, we use this cross-validation, so we save the data, but still we do not overfit on our hyperparameters, because overfitting can occur on the data itself, on the coefficients of the model. And it also can it can occur based on the hyperparameters. If we use our testing dataset to always check how the model performs, it will we will leak the data. We will manually overfit our model on our testing data. So after the training sequence is finished, you can see it took not a lot of time. We can see the results. So the best classifier, after we fitted our classifier, we can get the best one, because we ran through a lot of different hyperparameter combinations, and we use the best, the one that showed the best results here. And the best score that we achieved is 0.44. It's not, again, that good if you think about it. We have 3 classes, so it's slightly better than a random guess, but it's still an improvement from the previous step. So again, it's still better than the majority classifier. And here, as you can see, the F1 score is not strictly dependent on this one point. And the macro average F1 is much higher. We had 0.17, if I remember correctly. Okay, so the next step for us would be adding categorical features. First, we will encode them. We will encode the features into numerical ones. This can be done multiple ways. For example, you can take one column and index all unique category names with numbers and just replace them in a column. This is called label encoding. The key point here is that you can use label encoding when you have class 1, class 2, class 3, and you just write that, okay, it's 1, 2, 3. The problem here is that by doing so, you're implicating that class 2 is somewhat bigger than class 1, and class 3 is bigger than class 2. So if we talk about, I don't know, maybe cats, dogs, and stuff like that, if we have those species and we categorize them using label encoder, then we can end up that rabbit is for some reason is bigger than the cat from the point of view of the model, and the dog is smaller than the rabbit. I don't know, something like this. It is however, possible to use it if we have categories that codepend on each other. So if we take, for example, the education level, so we take beginner school, mid school, high school, college, university, and stuff like that. So we can arrange them in an order that makes sense. And in these cases, sometimes we can use label encoding. But usually the most common way to do it is dummy encoding. And what it does, it just takes all of the unique classes in the categorical feature and gives them a separate column. So if we have, for example, 4 unique values in a categorical column, we will end up with 4 new columns. Each one will be a binary one. And if in some case, if for our sample, if it corresponds to one of these columns, which are dependent on the class, then it will have a positive true value, and the other 3, or however they will have a negative one. The best part here is that if we encounter a new category that we did not see during our training sequence, we can just have all of them equal to 0, and it will not break our model. So we'll create a new dataset where we will add our categorical features. Just a quick, quick question: is everything fine? Everybody is keeping up? There was quite a lot of talking these 5 to 10 minutes. So if there are any questions, please ask them. Okay, so we've created this new data frame. So we copied it so we can process it separately. And now we will remove the application names because they're unique for each sample and they are basically textual features. If we encode them with dumb encoding, the unique features, it will lead us adding the same amount of columns as the amount of the dataset, basically, because all of the samples are different. Such features obviously will not work this way, so we will drop this column and we will proceed with the others, the categorical ones. As I said before, sometimes it makes sense to encode columns with label encoding, and in our case, content rating column is somewhat suitable for this approach. We can do it. Yeah, I'm not saying that it's definitely the best solution, but it's just an example that you can do it and it makes sense. So for content rating, we use label encoding and we specify exactly the order, because if we use the method, we might end up messing up the sequence. And for others, we just use then we replace our original content rating with the one that we just created. Now, for the remaining categories, we apply the dummy method. It's a dummy, get dummies. I don't know why they called it like so, but anyway. Now we added 44 features instead of 4 categorical features that we had before. Let's see how this works out. We again split our data because we have a new data set. And now the next task for you is to train a model, make a prediction on the test data, and output the statistics. And don't forget to measure your training time. You can look at the previous part of the workshop in order to help yourself on how to do it best. I will give slightly more time again for this task as it is quite big. If you finish the task, please write in the chat that you did so. Okay, guys, do you need more time? Okay, no problem. Okay, guys. Well, some of you are finishing the task. I will also talk about there is actually more than 2 ways to encode your categorical features. There are some of the less popular ones. For example, there's how is it called? Effects encoding, which limits the amount of columns that are being created, but it's somewhat controversial to use. One of the main ones that is also sometimes used, it is called target encoding. Target encoding basically takes the mean for the target variable. One moment, I will try to copy the image, and it's not working. Okay, so what it actually does, it takes for each category, it takes the target variable and calculates the mean for that target variable for that category, and replaces the category name itself for that mean. One of the key points here is that not only it does that, it also uses k-fold encoding. It's very similar to cross-validation, but slightly different. The fact is that it also uses different folds to calculate those means in order for the values not to be overfitted on one specific data set. You can also try that technique later on this data set. Maybe it will give you some better results than dummies shape. And again, the really nice part about this is that it does not create a lot of new columns. So the data set is not as sparse as it could be. Yeah, okay. So should we proceed? Did anyone finish the task? Okay. Okay, so what we do here? First, we set our random seed. By the way, I didn't talk about that previously, but it is actually really important while you are doing all this research to fix the random seed, so your results can be compared to each other. Because it does not happen very often, but sometimes different seeds can give a significant amount of difference between different runs, and it should be addressed separately. while you're tuning the model, tuning the data and stuff like that, you probably should fix it as it is. Now we again use our grid search CV pipeline, and we run our training sequence, and in the end we should get the results. It shouldn't take a lot of time. Yeah. So as you can see, we have our new best score. It is actually better than it was before. And if we calculate our metrics, you can see there is one interesting thing here. So definitely the in general the results are better, but they are not as the improvement is not as big as it could be, and the macro average did not grow a lot. But the most interesting part is that the weighted average that was, if I remember correctly, 0.51 for the basic model, we just took all of the majority, took all predictions as a majority class. It had almost the same value, and this is actually why I don't really like to use it, because we did all of this stuff. Our model behaves much better, but still this weighted average is it almost did not improve. Okay, so and again we append our results to our list so we compare them later. Next part is the feature generation. Here we will expand on our feature space by adding new features, manually crafted with love and care. First, we need a separate copy of the original dataset, again, so we can process separately. One of the things that we did before is adding a price per megabyte column. Sorry, we looked at the price per megabyte, and we saw that there is a difference where we do not have expensive and large applications. If let me just, if I be able, I can't remember where it was. So yeah, here it is. So if you remember, we have this blind spot, and again, it just tells us that there is some sort of sense to add this new feature, because there is some uncertainty. The distribution is not equal between on all. Is not evenly distributed on all of the feature space between these two variables. Then we also add logarithms for price and size, because if you remember, those were exponentially, those grew exponentially, and it's not really good for our linear model. Next part, it is always useful to introduce polynomial features from numerical ones. Let's make them from previously calculated logarithms of price and size. To do so, we can use the scikit-learn function polynomial features, and it just adds all of the features that can be obtained from these ones. So here it's obviously the degree 0, and then degree 1, 2, and 3. Sorry, 0, 1, and 2. It may seem like the model could be able to deal with such things by itself, but the funny thing is that not always. If you remember, logistic regression, it's a sum of our features multiplied by their coefficients. And there is a really simple example when it could not work as well. So imagine that for some reason we have a data set that should predict the price of an apartment. And instead of square meters, we have the length of X and Y for walls. So we don't know actually the square meters, but we know the length of the walls. And if we just use the logistic regression, then we won't have this multiplication. Obviously, that square meters are much more, they depend much more on our target variable, the price. But if we don't do it, we will not catch that dependence. This is why you always want to look at the data and find such combinations. Actually, one thing that you could use, we did not include this in this workshop as it is quite extensive and it works for quite a long time. But there is there is a framework called feature tools, and it gives you an interface to generate these combinations of features. You can tune how deep those combinations could be, what the relations you want to explore. But usually it's an overkill. And you can just look at the data and figure out for yourself what makes sense and what not. Now we have new columns and we need to attach them to our data set. Now you can see we have much more data than we did before. We will add the number of characters and the number of words in the title as features. Again, a really strange feature, but if you remember, we had a plot, a density plot that showed us that for some reason it does matter. And those applications that have short names, they are less likely to have good reviews. Now, the names of applications that contain a lot of garbage, and we should clean them most likely. Here we make them all lowercase. We replace all the special symbols, and everything that goes outside we replace with nothing. Now we can see how our clean text looks like after we did it. So as you can see, it's all very simple now. No uppercase letters, no parentheses, no special symbols and stuff like that. It's much easier for the model to process it that way. Now, after filtering, we can add the number of characters and the number of words as features. The next step would be to add the difference between the original number of words and symbols and the normalized ones. So for some reason, there are normalized headers that have more words than the original ones. And it is always important when you do something with your features, when you do feature generation, you should also check your new features that they are correct. And here we see that there is this problem that we do have this, well, it does not make sense. And let's just see why did it happen. And well, when we look at it, it makes sense. We had a lot of special characters, and after we replaced them with a spacebar, we ended up having a lot more words than we did in the beginning. Generally, everything seems fine, so we add our new column to the dataset, and we drop the previous one. Now we need to encode the categorical features into numerical vectors again, because this is a new dataset, a new copy, and here our categorical features, they are still the same. So this is the next task. Basically, this should be slightly easier, as we already did it previously. I think that after this task, we will actually make a break. The next part touches a slightly different topic, so it would make sense. So right now, the name was actually feature tools. Yeah, it's quite simple in that. So we're going to touch the subject of visualizing the data and a little bit more feature generation. So right now you can finish the task, and then the break will be from from 20 minutes past 12 to 30 minutes past 12. Again, I will be here and I will be able to answer all of your questions. There's not a lot of stuff. Actually, we need to talk about, but in my opinion, it is the most interesting part because we are getting close to the end and to the conclusion. So it's really nice that all of you who stayed, you made it through. I understand that it's quite a long time for a workshop, especially an online one. So I'm proud of you guys. I will turn off my camera for now, but I am here. Okay, guys, so the last segment, I hope that everyone is back at their working places. Okay, so the last task is here. So as I said before, here we replace our content rating. Yeah, 1 moment. Here we replace our content rating with label encoder that we used before, and we use the same getDummies function. Actually, I should note that getDummies is applicable here as a like educational moment, but you probably would prefer using the scikit-learn one-hot encoder because getDummies does not support the fit transform interface, and it could give you trouble if you're working with new data. So on projects that imply that you will be shipping them to production, it's better to use not getDummies, but so it's something like that. If I remember correctly. But here it doesn't make a lot of difference, but it's just a good thing to know and to understand. Regarding the question, have I ever tried to use standardization or normalization part of grid search base search? Could you elaborate, please, on that question a little bit more? I'm not 100% sure if I understand exactly what you mean. So did I use the standardization normalization techniques for base algorithms or so I hope that I understood it correctly. So in simple words, in simple words, usually it's just strictly always better to use standardization or normalization. I actually prefer standardization because it actually transforms the data and it sets its median in the zero, and then it distributes most of the data on both sides in the range of standard deviation. If something else comes, if some new sample comes that has like a big difference from what the model saw previously, it won't be such a big problem. But if we use the normalization function, it strictly limits the data in between 0 and 1. Yeah, the normalization uses something, always limits the data between 0 and 1, and it does not change the distribution itself. It only compresses the range. But with normalization, you might have some problems if you have some new value that differs a lot. It can break the whole pre-processing sequence. Not saying that it will definitely do something bad, but it's more risky. Standardization is more robust in this regard. Did I answer a question or not? Yeah, but you didn't. Standardization and normalization are applied to numerical features. There is no point on of applying it to categorical data. This would happen, but Boolean features as well as other categorical features, they are not standardized. Well, basically it is, because you have two possible values, right? 0 or 1, two categories. Okay, then we can proceed. Now we will get to the data visualization. For now, here we will use the UMAP algorithm. Again, it is strongly advisable to standardize the data before using this algorithm, because it will really affect how long it works. This is, well, at this moment, it is not already a new algorithm. It's quite well established. But previously, before UMAP, the most popular algorithm for these purposes was TSNE. However, UMAP is better in almost every way. It has no restrictions on the dimensions of the original feature space. It's much faster and it's more efficient. So let's see how it works. First, as I said, we standardize the data, and then we create our UMAP. As you can see, we have a fit transform interface here, but it is somewhat deceptive, because the way UMAP works, the fit transform interface is not working 100% correctly. So you might end up getting different results for what you input after you train the algorithm. But basically, it is a semi-machine learning algorithm. It is quite complicated in terms of how exactly it works. But what it is used for is transferring the data from our high-dimensional space into a two-dimensional space or a three-dimensional space, so we can create, so we can plot it, and we can look at it, look at the whole data set at one point. As you can see, what it does, it tries to match the data on the two-dimensional space while keeping let's say, the distance between the samples in the original data set, in the original high-dimensional space. And here we can see quite a lot of clusters, which also, something that you should take notice of. So sometimes when you will build something like this, you will just see a completely random blob of different samples. But here there is something to work with. To actually take advantage of what we saw here, we can apply a clustering algorithm, a clustering analysis to separate these groups. And this is why these visualization techniques are so important, because you cannot comprehend a high dimension like 10D, or even you don't understand that there could be like 100 dimensions in a dataset. And you will not be able to comprehend how the data is allocated among itself. Of course, it is an approximation, and of course, we miss out on a lot of data, but still it's better than nothing. And we see some clusters, and so we can use the clustering analysis. Here, there is, a solution we had to come up with, because for some reason, the Colab works in a slightly different way. It processes the data in a slightly different way, and it gave slightly different results from what we had when we ran it locally. So, in order for the results to be consistent, we added this part of the code that we will not go super deep into. But the main part is that we use the file, the data that we upload from the GitHub, and it is a pre-calculated clustering model. So after we load the model, we can see how the clustering algorithm went. We use the k-means algorithm. There are, of course, different ones. There is dbscan, where you do not have to specify the amount of clusters you want to achieve. But we just, for now, we used a more simple algorithm, the k-means, and we used 30 clusters. Now we have a really, really colorful representation of our data, but what can we do with it? Well, again, we can get back to analyzing our distributions. So we can compare all of the different clusters between themselves, and to see if there is a difference in how the target variable is distributed among them. And as you can see, there is actually a huge difference between how different clusters can behave. Of course, not all of them. For example, cluster 5 and cluster 8, they're very, very similar. But if we look, for example, at cluster 1 and cluster 3, you can see that it's actually, there is a huge difference between them. And if we look further, you can see that there are some variations. And what it tells us is that we can use these clusters as features too, because they differentiate the data. This can be done with the following code, where we drop again our target column, and we add our cluster as a categorical value, where we just add cluster 1 to 29, and then we apply the get dummies again to it. So now, if we look at our algorithm, we now have 84 features, including, just 1 moment, I will do it here. We have quite a few features, including the new ones, the categorical ones. So as you can see, all the clusters are in here. And also you can see, okay, how one-hot encoding works. So the first two rows are in the second cluster. Okay, so it also would be possible to use aggregational features, as I said before, and use different mathematical operations, something like, algebra and geometry functions, cosine functions, stuff like that. But it's actually, a very tedious process, to be honest. And usually you don't have to go that deep. It's very rarely when the model needs that much of a help. But sometimes, if you know, for example, that some features should behave in some way, it's better to use some of these mathematical operators. And yeah, it's about feature tools. So we did quite a lot. Of actions, big amount of work, and we now can see if it all paid off. For your next task, you will have to split the data set and the target variable into training and test set, train the model, make a prediction on the test dataset, and output the statistics. And don't forget again to measure your training time. So just a couple of more minutes if in case somebody did not finish the task, and we will proceed. Okay, so let us proceed. So again, in general, the code is the same as we had previously. The only difference here is that we added the train test split for the current folder. As you can see, we did add a bunch of new features, but the improvement, though there is an improvement, but it's not as big as it was before. And it was actually somewhat deliberate when we took this data set. It's not that easy to deal with. It's not easy, to get a 90% accuracy. You will encounter these situations when you will hit the ceiling, and each additional step, each additional percent will require a lot of work. There is this very famous principle, Pareto principle, that you will get 80% of the result by applying 20% of your efforts. And after you get that 80% of the result, it's life starts to be really hard. Okay, but anyway, we did get an improvement, and we also append our new results. Now, the final part of the data processing sequence is the dimensionality reduction. Usually, you want to know what features are actually doing the work and what features are not, because even if the feature does not give you anything positive, if it doesn't have any useful information, it can harm your results, because still there might be some false correlations, and it can shift the result of your training and testing models. So here we have actually only 86 features. It's not a lot, but there can be tens and hundreds of thousands features. Well, those are extreme cases, to be honest, but a couple of hundred features is actually very common. The main goal is to reduce the dimensionality of the feature space and not lose useful information. So there are a lot of ways to reduce it. You can use statistical methods of dimensional reduction. The most common one, I think, would be principal component analysis, PCA, and linear discriminant analysis, sometimes factor analysis. You can use machine learning-based algorithms, TSNE, UMAP that we've talked before, and methods based on feature selection. Feature significance determined by the training of some models. Filtering methods, lasso and ridge regression. Well, basically lasso. Ridge is not exactly correct here. Lasso can filter, ridge cannot. And the grid algorithm, where we add or remove features step by step. Also, you can use autoencoders as a method of reducing the dimensionality. We will look at the principal component analysis and backward feature elimination. So PCA is really, really popular. And the challenge of principal component analysis is to find subspaces of smaller dimension. The words here are quite complicated, but basically what it does, it tries to transfer our data in a different dimensionality where each component starting from the beginning to the end, it tries to explain as much variance as it can. And the further we go, the less variance each component describes. What it leads to usually is that, for example, if we have 86 features and we use PCA, we can use much less components of the PCA to contain and to explain the same amount of information. And apparently, most of the information can be saved within the 60 70 new projections components. Actually, the last step here is not really big, but it depends. You can actually stop somewhere around 45 or 50. So now let's see how many components do we need to keep 99% of the original dataset information. So here is a very important part that 99% of the original dataset information implies 99% of the explained variation. And when you're applying the PCA method, you can set the number of components you want to leave. And if you set it as an integer, then you will leave exactly that amount. If you leave a float from 0 to 1, then it will leave the amount of the percentage of components that explains the specified amount of variance explained by the model. About the logistic regression and what exactly we're using. As I said before, in data science, one of the main principles is trash in, trash out. So if you give the model bad data, it will very likely give you bad data on the output, bad results. And it's, of course, it depends. And some algorithm would perform better than the logistic regression. But you would be surprised how little actually it affects compared to a good data pre-processing and analysis. So, of course, other algorithms, there are algorithms that will be able to give better results, but they are slower, and this is one of the reasons that we stick to logistic regression here during the workshop. And again, it's not as important for them. It's not as important what data do we use. It's more important what algorithm we use. It's more important how we pre-process the data. Okay, and now for the task. So please apply the PCA algorithm to the def new dataset and leave the amount of components that explain the 99% of the variation. This task is not as complex as the previous one, so let's say we'll take 3 minutes and we will continue. Okay, we'll speed up a little bit so we can finish the workshop in general. So here, as you can see, we set the n components to 0.99, and the result shows, the PCA data shape shows that it is enough to leave only 48 components to explain 99% of the data variation. It can be really important in cases when the model performance in terms of processing power is crucial. So next comes the greedy selection. This is actually the most reliable, and I am even gonna say the only reliable way to find the features, to filter the features that do the main job. It is very resource intensive. It's basically brute force. What we do here is we remove one feature at a time. For example, we have 86 features, and we, one feature at a time, remove each one of those features, determine which of these features performs worse. So some features will definitely affect the model in a bad way. And we remove that feature, and we leave, we're left with 85, and so on and so on. And as you can imagine, it is quite expensive in terms of time. So here we will not launch, and I ask you not to launch that part of the code right now. You can do it later. But basically what it does is, as I said, it just goes through all of the possible variations, and it step by step removes those features. Now, we do have a pre-processed file where we have the results of that process. And as you can see, in the beginning, I think the first 40-ish features, it actually slightly goes a little bit up. And all of these features, we do not need them. But here, from the 40th feature, we start seeing a huge drop. So here, the most point significant features are actually the ones that were removed in the end. And if we look, we can see that the length of the clean text title is the most important feature that gave us the biggest result. It's actually really hilarious to me. Yeah, okay, so greedy selection, it is an algorithm that allows us to process our features in a loop and throw out those features that affect the model the worst. So for example, if you see, we start over here, we have 0 features thrown out. The first feature that we threw out is actually made things worse, as the score, after we removed it, it became better. And this is the main point. Feature importance, if we're talking about, for example, random forest, it does have a feature importance method. But the funny thing is that it takes feature importance as, so basically, if the feature, when the trees are, when the branches are divided in the tree, if a lot of features are divided by a certain feature, it is considered to be important. But it does not matter as much. A lot of times you will see smaller features that make the difference in the end. So I actually did encounter cases when I removed the most important feature that I got from the feature importance part, and the model became better, became showing results better than it did before. So the only reliable way is this one, but it is very expensive in terms, it's really long, especially if the model is heavy. So as you can see, we also have some operations that we applied, for example, the square of log size. So it just shows that sometimes it is important to apply such things. We can see a couple of clusters over here. So everything we did is actually was worth it because the model uses it and it gives the biggest profit. Now let's find at what stage was we had the best accuracy, the best score. And it was on the 39th iteration. So we can leave 47 features. Here we save those features, and here you will have, I think it is the last task, if I remember correctly. Yeah, it's the last task where you have to take the greedy features and train the model on the features obtained by the grid selection method and the PCA method, both of them. And then you should add the results to the table. This task is quite big, so I will give you more time, something between like 10-15 minutes, so you can all finish it. And then we will proceed. So the tasks here is for the grid features and here for the PCA features. Okay. If you have questions, again, please ask. Okay, so let us proceed. And the last part is as follows. I hope that you were able to solve at least the first one. I understand that there is a lot of code. Here we train our models. Yeah. So we train both of our models and we calculate the metrics for them and append them to our results. So after we did that, we can get to our conclusion. So as you can see, here we have a list of all of our data, how we applied it. Mostly it goes up in terms of test score, but actually the best model in terms of test is the one with the manual features, the biggest one. Okay, goodbye, Akshay, no problem. By the way, until everybody left, it would be great if you would leave, if you like the workshop, if you leave a review later. It would really help a lot. Okay, so the test score is actually the best for manual features and the validation score is the best for grid selection. We do have a slight overfitting over here, but it's not too big, though there is something to consider when dealing with this one. There's also one thing that should be noted, that the learning time, how long the model was learned and how long it took for the model to make predictions. And considering everything, all of the aspects, you could argue which of the models, the manual features or the grid selection is better. Also, PCA is also looking quite good, but it's worse than both of those. And it works longer. Actually, with the PCA, there is one more problem. It's actually, it really overfits a lot. It's really not robust. It's really bad with overfitting, so you should treat it and use it carefully. So the model trained on the feature on the PCA, it's okay. Yeah, it should be all. So now we can't actually say that one approach is 100% better. It depends, and in a lot of cases, grid selection can significantly improve the result, but it takes really a lot of time. You should really think twice before using it if your data set is huge, because we only have 10,000 samples and not a lot of features. PCA is quick, but it overfits. And well, you might as well just leave the manual features and let the model decide what is better. One more thing that I wanted to talk about, and I was not sure if we would have time. It is about explainable AI, explainable machine learning. And it is a very complex topic, specifically if we're talking about, such complex algorithms like neural networks. But otherwise, for logistic regression and decision trees, it's much easier. And more than that, there are two frameworks. One of them is called SHAP. The other one is called LIME. I will write them. So. SHAP and LIME. These two frameworks are specifically designed to get estimations of how different features affected the training. They work in a slightly different way. And there are different approaches on how to estimate that. So some, for example, features, some approaches, they do not require you to actually train the model. You just try to manipulate the data and see how it affects it. In other cases, you can train the model, and then you can add some noise, make predictions, and yeah, you can add some noise, make predictions, and see. Okay, I shifted this value this much, and it affected the results. The result as follows. These two algorithms can be really useful again when you're going with the development stage, because it will sometimes show you the right direction where you should maybe put more attention with your feature engineering. But also it can be used further in the production part and help you extract those dependencies, the importances of features for each prediction. Now, as I said, also there are different algorithms that you can use. We did add them over here. We used random forest, gradient boosting, XGBoost, CatBoost, a lot of boosting algorithms actually. I really don't like using neural networks on structured data because, well, 99% of the time neural networks will take like 3 or 4 times as much as classical algorithms, and they will not outperform them. Neural networks are really good when they're working with specialized data, like text or images. So we did try multiple different algorithms, and the results here, as you can see, they are slightly better, so better than logistic regression. And as I said, yeah, it does make a difference, but it's not, like from 54 to 90. It just shows how much it is important to pre-process the data, and then you can do all of the manipulations with the algorithms you want. In general, this is all. We have 10 minutes left, and if you have any questions, you can ask them. Or otherwise, if you don't, then thank you a lot for staying for such a long time. I do understand that it is hard, and I do hope that you enjoyed it. Okay, that is really nice to hear. So if you will have access to the workshop later, if you have any questions, I'm quite sure that my contacts should be in the description. If you have any questions, you can ask them later if you have some. And again, if you did like the workshop, it would really mean a lot if you left a good review. But yeah, then thank you all a lot, and maybe see you next time on some other conference.
Thank you very much to all.
Yeah, and thank you, Aleksandr, for helping me during the workshop and answering all the questions. Okay, then goodbye. See you all.
Bye-bye.